So in this video, we're going to briefly review reaction stoichiometry. And you might remember that stoichiometry just means calculations involving the amounts of substances. And in particular, we're going to review one very common type of reaction, which is where we're going to convert grams of one substance into grams of another substance. And the key tool in being able to do this is a balanced chemical equation. Okay, let's see if I can show you what I mean. So for a given substance, we know that the relationship between the number of particles of that substance and the moles of that substance is Avogadro's number. That's the key thing there that's going to help us convert between those two quantities. We also know that we can convert between the moles of a substance and its mass in grams using the molar mass. That's great too. More recently, we've learned that we can relate the moles of a substance and its volume in a solution via the molarity. And so Avogadro's number, molar mass, and molarity are kind of our key quantity for converting into and out of the moles of a substance. So this is all for a single substance. What happens when we have a balanced chemical equation where we've got like multiple substances? So when we have a balanced chemical equation, we know that we have coefficients that indicate the amount of reactants that are being consumed and the amount of product that is being produced. So when I look at this balanced equation for the combustion of methane, what I'm being told is that 1 mole of methane is consumed for every 2 moles of oxygen. Right? I'm also being told that for every 1 mole of methane that is being consumed, 1 mole of carbon dioxide will be generated and 2 moles of water will also be created. This balanced chemical equation is also telling me that for every 2 moles of oxygen consumed, 1 mole of CO2 will be produced, or alternatively, for every 2 moles of O2 consumed, 2 moles of water will be produced. So yeah, they're telling you how much reactant's getting used up and how much product is getting produced, right? That's it. So yeah, that's the cool thing about balanced chemical equations. So what this means is we can use those reaction quotients, the reaction coefficients, to generate what are called mole ratios, and they allow us to convert from moles of one component to moles of another. So we had this guy before, and how we can create these mole ratios is by looking at these coefficients. We can see here that for every 1 mole of methane, I will require 2 moles of O2. Or you can say for every 1 mole of methane, I will produce 1 mole of CO2. So using the coefficients, there's imaginary ones here, isn't there? In this way, to generate these things that we call mole ratios allows us to convert from moles of one thing, perhaps it's O2, into moles of another thing, perhaps it's H2O2. And how we're going to do it, how our the mole ratio that we're going to use is the coefficient of what we want divided by the coefficient of what we're given. Okay, so we always have what we're trying to eliminate on the bottom line and what we're trying to generate on the top line of our conversion factor. So here's a good example. It says if 3 moles of iron is reacted with O2, how much Fe2O3 is produced, and it gives you the balanced equation, right? So I want to go from moles of iron to moles of Fe2O3. So what I got to do is I got to multiply by the conversion factor that has moles of iron on the bottom, so that's going to be 4 moles of iron, and then moles of Fe2O3 on the top for every 2 moles of Fe2O3. I started with 3 moles, so you can see that works. There you go. So 3 times 2 on 4, very obviously 1.5. Okay, so some of these things, you can kind of do in your head, but it's always just worth writing it out and cancelling your units and not dropping significant points because you got things wrong. Okay, so always use your conversion factors. Don't do things in the head. Cancel your units and make sure you really do have the units remaining that you want. Okay, so we can combine our mole ratios with other types of conversions that we've been doing. So for example, we can combine them with a grams to moles conversion. So we can do something like this. We can go from grams to moles. Maybe we go from grams of A to moles of A. Then we can use our mole ratio, go to moles of B, and then finally we could go back out to grams of B. So we do stuff like that all the time. So this problem gives the question in terms of the moles of one of the reactants. So it says if 26.08 grams of methane is burnt completely in air, what mass of CO2 will be produced? So the first thing I'm going to do is calculate, or is to convert, how many moles of methane I have, and to do that I'm going to multiply by 1 on the molar mass. So 26.08 grams of methane times by 1 mole of methane, and in here I'm just calculating a molar mass, comes out to be 16.05. So 26.08 times by 1 on 16.05, you can see grams of methane cancels, and it leaves me with moles of methane. So from my balanced equation, I know that for every 1 mole of methane, I get 1 mole of CO2. So I'm kind of laboring this point here, but I'm going to apply my mole ratio to convert from moles of methane to moles of CO2, just like we were previously. So I want to have the coefficient of what I want on the top and the coefficient of what I'm trying to eliminate on the bottom of my mole ratio. So here I go, 1.626 moles of methane multiplied by 1 mole of CO2 per 1 mole of methane, and moles of methane, you see, cancels out, leaves me with moles of CO2. Surprise, surprise, it's exactly the same as my moles of methane. It's not really that surprising because they're in a 1-to-1 ratio, right? So what am I going to do now? Well, I got moles of CO2. I'm going to go on now and turn my moles of CO2 into grams of CO2. And how I'm going to do that is by multiplying by the molar mass, because we know the mass in grams is equal to your number of moles times by the molar mass. So here we go, 1.626 moles of CO2 times by, and this sum here is just calculating the molar mass, turns out to be about 44.01 grams of CO2 in 1 mole. So moles of CO2 cancels, leaves grams of CO2, and there's my final answer. So you're probably aware that both methane and CO2 are greenhouse gases, and you might have heard that combustion of a hydrocarbon is a major cause of production of carbon dioxide, and you can see that happening here. I take a little less than 30 grams of methane and I turn it into a little more than 70 grams of CO2. Okay, so there we are. Now what do I also get from this process? Well, you can deduce here that this is going to create a bunch of heat because the water is coming off as gaseous water, isn't it, right? So why do we burn methane? To generate heat that we use as an energy source. And methane is also commonly known as natural gas. Okay, here's another one where we have a different balanced equation, one that we haven't seen before. It says if 33.08 grams of this substance here, it's called ethene, is burnt completely in air, what mass of CO2 will be produced? And they very nicely give you the balanced equation. And again, you can see that we're making gaseous water, so we know that this guy is producing a lot of heat, which is not surprising because they describe the reaction as a combustion reaction. So we're going to do the same process. We're going to go from grams of C2H4 to moles C2H4 to moles of CO2, and then finally onto grams of CO2. So in my first step, I'm going to calculate my number of moles of C2H4. I'm going to take my mass in grams and multiply it by 1 on the molar mass. Okay, and then that gives me my moles of C2H4. Generally, molar masses are really easy for you because you have access to a calculator, or they're going to be given to you, so you don't need to be worrying about calculating them individually each time. Okay, so from my balanced equation, what I know is that for every 1 mole of C2H4, I get 2 moles of CO2. So I'm going to apply my mole ratio to get my moles of CO2. So multiply it by the conversion factor that has the coefficient of what I want on the top line and the coefficient of the substance that I'm trying to convert from on the bottom line. So 1.17 moles of C2H4 times 2 moles of CO2 per 1 mole of C2H4. And again, those numbers are just coming from my balanced equation. Okay, so I get 2.358 moles of CO2, and then finally I have to convert my moles of CO2 into grams of CO2 because they asked for mass, and I'm going to do that by multiplying by the molar mass. So 2.358 moles of CO2 multiplied by 44.01 grams of CO2 in 1 mole, and again you can see that the moles cancels out and leaves me with the grams that I want. So this is a process that requires 3 conversion factors, 2 molar masses and 1 mole ratio. So kind of making this a little bit more streamlined, whenever we're trying to do these what we sometimes call grams of A all the way over into grams of B, after we've done a couple of these like we just have, you fairly quickly recognize that you're multiplying the same 3 conversion factors together every single time. You're going to take the mass that you were given and multiply it by 1 on its molar mass. And that'll give you the moles of what you were told you had at the beginning. Then you're going to multiply that by the mole ratio that has the coefficient of the substance you're interested in on the top line, divided by the coefficient of the substance that you're converting from on the bottom line. And then that'll give you the moles of the substance that you are curious about. And then finally what you have to do is multiply by the molar mass of your substance that you're interested in. And so basically that's what you're going to do. So you're going to take grams of A, multiply it by 1 on the molar mass of A, multiply that by the number of B's over the number of A's according to your balanced equation, and then finally you'll multiply that by the molar mass of B. And so in order to be kind of like quick enough at the Gen Chem level to be able to do these conversions, you're going to do that whole thing on one line rather than doing one calculation here, one calculation here, one calculation here. So what I like to do when I'm presenting with one of these problems is I immediately know I'm going to need both my molar masses, so I go away and get those. And then I make sure my equation is balanced so I can get an accurate mole ratio, and then I just go for it. All right, and multiply those 4 numbers together, and it works like a charm every single time. So here we go. This is an example. It says if 3.08 grams of methane is burnt completely in air, what mass of water will be produced? So I know that I'm going to need my molar mass of methane. That's 16.05 grams per mole, and I'm going to need a molar mass of water, and that's 18.02 grams per mole. I also know that I'm going to need my mole ratio, and I get 2 mole of water for every 1 mole of methane. And so now I just have to put it all together, right? So I'm going to do grams of methane, there it is, multiplied by 1 on my moles of methane, and that gets rid of grams of methane and it gives multiplied by 1 on the molar mass of the methane, and that gets rid of my grams of methane and turns it into moles of methane. Now I'm going to multiply by my, so use that guy, multiplied by my mole ratio, and I get 2 moles of water for every 1 mole of methane, and that gets rid of my moles of methane, leaves me with moles of water. And then finally I'm going to use that one. Finally I'm going to multiply by my molar mass of water, and so what that does is that eliminates my moles of water and turns it into grams of water, and there I am, I'm done. So burning 3.08 grams of methane gives me 6.92 grams of water. So yeah, that's it. That's how it happens, right? So they're all kind of the same. So let's have a look at one where we kind of go back the other way. In this problem, it says how much Fe2O3 is required to produce 5 grams of iron. So in this case, you know that you want 5 grams of that guy, and you're trying to figure out how much of that you're going to need. So it's kind of like going shopping, right? You got 4 members of your family, and you're trying to figure out, how many pounds of ground beef that you need to buy to make that awesome lasagna that's going to feed them all. So you kind of do the calculation backwards. You know where you want to end, and you have to figure out how many ingredients you're going to need. So it's going to be the same thing. It's going to be grams of iron times by 1 on the molar mass of iron times by the numbers of Fe2O3s over the numbers of iron from our balanced equation, and then finally it's going to be multiplied by the molar mass of Fe2O3, and that'll give you the grams of what you want. So it's always just multiplying 4 numbers together. So 5 grams of iron multiplied by 1 on its molar mass converts the grams of iron into moles of iron. Now, so we've done that step. Now we multiplied by the stoichiometric coefficient of the Fe2O3, which is 1, divided by the stoichiometric coefficient of the iron, which is 2. So we get 1 mole of Fe2O3 for every 2 moles of iron. So moles of iron leaves us with moles of Fe2O3. And then the final step is to turn the moles of Fe2O3 into grams of Fe2O3, and we're going to do this by multiplying by the molar mass. So there we go there, and that leaves us with the units that we want. So we're going to need 7.15 grams of Fe2O3 in order to make 5 grams of pure iron. It kind of makes sense that the mass went down, because in this reaction what you're doing is you're eliminating the oxygen from the iron, so it's going to leave you with less mass. Okay, so that's a brief review of how to do the grams of A to grams of B conversions. That's going to be the cornerstone for us doing a whole host of chemical calculations.